Quantum physics has a reputation for being complex and difficult to grasp. Richard Feynman, the Nobel laureate known for his work on quantum electrodynamics, once remarked, "If you think you understand quantum physics, you don't understand quantum physics." This statement can be disheartening, as even Feynman himself acknowledged the challenges of comprehending it. However, it is important to note that this quote can be misleading. In reality, we have a solid understanding of quantum physics, which is arguably the most successful scientific theory to date. It has enabled us to create technologies like computers, digital cameras, LED screens, lasers, and nuclear power plants. After all, we wouldn't want to build a nuclear power plant without understanding how it operates. Quantum physics is the branch of physics that describes the behavior of the smallest constituents of our universe: molecules, atoms, and subatomic particles. These entities operate differently from the macroscopic world we are accustomed to. It is fascinating to realize that everything around us, including ourselves, is governed by quantum physics. While we often depict protons, neutrons, and electrons as particles, quantum mechanics describes them as waves. It's worth noting that quantum physics and quantum mechanics can be used interchangeably. They refer to the same concept. Instead of visualizing an electron as a discrete particle, we represent it as a wave function, which is an abstract mathematical description. However, this wave function doesn't represent a physical wave like those on water or in sound. It serves as a mathematical tool to calculate properties such as position and momentum. For example, to determine the position of an electron, we square the amplitude of its wave function, resulting in a probability distribution that indicates where the electron is more likely to be found. When we measure the electron's position, it manifests as a particle within the designated area. Therefore, in quantum physics, we can only predict probabilities rather than knowing precise details. This departure from classical physics, which operated on deterministic principles, is a fundamental aspect of the quantum universe. It's important to note that the wave function, representing the quantum realm, remains unseen, while what we observe is the transformation of waves into particles. This transition occurs through the process of measurement, which we refer to as the collapse of the wave function. However, we lack a complete understanding of how this collapse occurs, an unresolved problem known as the measurement problem. This is one of the challenges alluded to by Feynman in his quote. Another perplexing aspect is the dual nature of particles and waves. An electron, for example, appears as a wave until it is observed, at which point it behaves as a particle. This phenomenon is called particle-wave duality and can be demonstrated through the famous double-slit experiment. Imagine spraying paint through two openings in a wall. You would expect two columns of paint on the opposite side. However, on a quantum scale, when firing one electron at a time through the slits, we observe an interference pattern of stripes on the back wall, similar to what we see with waves. This suggests that the electron wave simultaneously passes through both slits, with the overlapping waves determining the likelihood of finding the electron at various positions on the wall. The question then arises: what happens to the spread-out electron wave when it undergoes measurement? It seems to transform from a wave into a localized particle. Yet, quantum mechanics lacks an explanation for this wave function collapse. This phenomenon extends beyond electrons and applies to everything in the universe. Consequently, the double-slit experiment has profound implications for our understanding of reality. Physicists have proposed various interpretations of quantum mechanics to explain these results and provide possible explanations for the behavior of quantum systems. Some interpretations suggest that the wave function collapse is a real physical process, while others propose that it is a result of our limited knowledge or interaction with the system. One interpretation is the Copenhagen interpretation, which was developed by Niels Bohr and his colleagues. According to this view, the wave function collapse occurs when an observation or measurement is made, and the system's properties become definite. Until then, the system exists in a superposition of all possible states. The Copenhagen interpretation emphasizes the probabilistic nature of quantum mechanics and the role of the observer in the measurement process. Another interpretation is the many worlds interpretation, proposed by Hugh Everett III. It suggests that the wave function collapse doesn't occur but rather leads to the branching of multiple universes. In this view, every possible outcome of a quantum measurement actually happens in a different universe, and we perceive only one of them. This interpretation aims to resolve the measurement problem by removing the need for wave function collapse altogether. Other interpretations, such as the pilot wave theory, also known as Bohmian mechanics, transactional interpretation, and objective collapse models, offer alternative explanations and attempt to address the measurement problem in different ways. These interpretations introduce additional elements or modify the fundamental principles of quantum mechanics to provide a more complete description of reality. It's important to note that these interpretations are not currently testable or proven beyond doubt. They represent different philosophical perspectives on the nature of quantum mechanics. The mathematical framework of quantum mechanics, however, has been extensively tested and confirmed through numerous experiments. Quantum mechanics, despite its conceptual challenges, is an incredibly successful and accurate theory that underlies many technological advancements. In summary, while quantum physics can be conceptually challenging, it provides a powerful framework for understanding the behavior of particles at the atomic and subatomic scales. It involves the representation of particles as wave functions, the probabilistic nature of measurements, and the intriguing phenomenon of particle-wave duality. The measurement problem and the various interpretations of quantum mechanics continue to be topics of active research and debate among physicists.